I guess people will be coming in as we start. So welcome to the very last Asia Q&A session on the last day of Neuromatch Academy. I'm the panel host for this session, and it's a little bit shorter than usual and a little bit of different time. So, but hopefully we'll have a few people are piling in as we speak. So why don't we start with quick introductions? I guess I'll introduce myself first. My name is Jeff Erlich. I'm an assistant professor at NYU Shanghai, and I mostly focus on rodent decision making, but I have been dabbling in a little bit of recurrent neural networks and training them like we train the animals to try to understand processes through RNN. Okay, so Marco, do you want to introduce yourself next?
Sure. Hi, everybody. I'm Marco Brigham. I manage R&D for a small Belgian startup called Manoia that is specialized in automated document recognition. I still do some research in neuroscience and also in sleep. That's it.
And we have Professor Kenji Doya.
Hi, so my name is Kenji Doya. So I'm now at the Okinawa Institute of Science and Technology. And we usually run Okinawa Computational Neuroscience course, but yeah, we don't have that. And instead, I'm happy to be able to join here. So it was the time of the so-called PDP, the time of first boom in the backprop when I was doing a PhD. And one of the things I worked on was use kind of an autoencoder for dimensional reduction of neuron model. Like, for example, compressing a 4-dimensional Hodgkin Huxley into 2-dimensional Fitzhugh-Nagumo type neuron model, or even more complex bursting models. So I worked on the autoencoders in those days, but it's already nearly 30 years ago. So I think there has been a lot of progress these days. And then I look forward to hearing you guys. How did you find about the autoencoders and other deep learning? Yeah, okay.
Our final panelist is Emtiyaz Khan, also in Japan. Do you want to give a quick intro?
Yes, so yeah, my name is Emtiyaz Khan, but you can call me Emti. It's easier to remember. And I am working at the Rick Hen Center for AI project, and I lead a team on approximate Bayesian inference. And I'm not really mainstream deep learning person, but I have been, hanging out with people who did deep learning since like starting of my PhD. So I'm lately, for last 4 or 5 years, we have been doing lots of deep learning, and I really don't know much about neuroscience, but but some of my work actually is being used in by neuroscientists. So I have learned some things about spike trains. So I was happy to see the lecture today, that there is some familiarity with some of these things. I think the stuff that was in the lecture, it's like a proximal algorithm that I have been using for a long time. So I know some things about that. So that's my background.
Okay, great. So before we get to the questions, I just want to make a quick announcement to remind all the attendees that they should do their daily responses. And after the Q&A is finished, they will do a somewhat longer course evaluation process before they start their project presentations. Okay, so I think we have a couple questions already in the Q&A panel about autoencoders. The first question is about this bottleneck thing. So there's fewer RGCs, retinal ganglion cells, than photoreceptors and neurons in V1. Right, there's more neurons in V1. Is this a natural autoencoder? And is center surround receptive fields an efficient way of summarizing visual stimuli? Or, okay, well, do any of us work on vision?
Not really.
Not really. I mean, yeah, I don't think any of us are really an expert on this. I mean, it's true that whenever you kind of have like a bottleneck and then an expansion, one sort of naturally thinks of the structure of an autoencoder. Well, I guess you don't know if it's an autoencoder. I mean, it depends on what we believe the brain is doing. I think a few people think that the brain is more about prediction than encoding. And so it's like a one step forward autoencoder, right? Like you're trying to find a low dimensional representation of the stimulus, which allows you to predict what the stimulus is going to be at the next time step, maybe. And I think, I mean, the center surround thing, it's pretty efficient because it's like allows you to do edge detection very easily. So, you know, we know just from like JPEG encoding or any kind of compression algorithm, if you have some constant information, you don't need to encode it as a bitmap. You can just track where the edges are. So center surround is a kind of a way to build up edge detection early on and let you encode the differences rather than the absolute value of stimuli, right? I think that's the general idea.
Mm-hmm.
Anyone else want
to? I like this question because I'm not a neuroscience person, and I was just thinking, is there an evidence that the brain actually does some kind of compression, some kind of bottleneck?
So I'm supposed to click a button. Neuromatch Academy is going to answer the question live. Can you hit answer live? Oh, I see, answer live. Oh, I see. Okay, I didn't really. I'm just slow on the tech. Okay, yeah. So the compression is really, compression is an interesting topic. I mean, autoencoders are a form of compression, right?
Mm-hmm. Mm-hmm.
But it's a form of compression that allows you to do operations on the compressed data, probably.
Also, attention is in a way a sort of compression.
Mm.
When you,
it's lossy compression.
Right. And since we need to attend to things, to focus on one aspect or another aspect of stimuli, it's I think that's kind of a clue that the brain is some way compressing data, right? Mm. That we cannot normally like attend to everything, to all the stimuli that we're receiving. So it's kind of selecting, and it's lossy, as you say. Jeff.
Because on the math side, if you look at all principles, all models, you know, most of them are doing some sort of bottleneck or some sort of compression, and that's like the principle of encoding information. Mm-hmm. So on math side, it's definitely clear. On machine side, that it should be compression. But on brain side, I'm not sure if that's but I think it's very likely, right?
Mm-hmm. Right. Mm-hmm. Like from a mathematical perspective, go ahead, Kenji, go ahead.
If you look into the visual cortex, the B1 has the largest number of neurons, and the B2, B4, and even the entorhinal cortex to the higher hippocampus, the number of neurons would be gradually smaller. So one way to look at it is a kind of a compression, but also probably different areas look into different dimensions or features, right? So for example, some cortical areas specialize into object identity. Some areas like MT or MST analyze their location and movement. Right? So I think there's a compression and also extraction of a different dimension or features of the image would be going on in the visual cortex.
Makes sense.
So we have a next question is, what types of constraint are used in neural networks to extract latent representations other than autoencoders? So the classic deep network like ImageNet and these other convolution neural networks, they do generate latent representations and they're not autoencoders, right? They're classifiers trained to identify objects by label, but because they have different stages of processing, you can think of each layer having a different latent representation. So I think that that's pretty straightforward, that any kind of layered network will have latent representations all along the network, and regardless of whether it's an autoencoder or a classifier or other unsupervised learning algorithm.
Mm-hmm. And we can see this as we build these deep networks. Like if there is, let's say we already have some layers and they already are doing some processing, and as we go deeper, this higher level sort of processing, and then when we add a new layer, if this layer is adding something to the network, for say for classification, if you have a classifier, then this new layer will attend to a different or to some added value in terms of abstract processing of information. When you add a new layer and it's not doing anything, then, well, either it's something, it's how you build the network or some technical detail, or just there isn't, there's much more to extract from the data to do, so in this case, a classification task. But like every layer, it's processing one aspect of the information, and we consider that as a latent space.
Yeah.
In a way, I found GANs to be a different way of doing representation learning. So that's one thing that comes to my mind. Although they never claim that anybody's doing representation learning, right? I mean, there is very little work on representation learning, but somehow it's learning something inside, and it's not an autoencoder framework.
Yeah.
Right.
And it's learning the data. It's really learning the data domain.
Were GANs covered in NMA at all? Oh, I just got.
Yeah.
Saying no.
Not in our DL2, no.
Okay, so I guess maybe you might want to just mention what a GAN is.
Oh, so generative adversarial network, and I really don't know much more than that. But it's basically like there's two networks there trying to compete against each other. So the loss function is not written as a minimization of loss like what you have seen in the lecture. Like minimization over H and X is what was in the lecture. But there it's like min over one quantity and then max over another quantity. And then there are two networks, and they are trying to, one is trying to give the example, which is adversarial, and the other one is trying to classify it. And somehow when you do this, then the generative network is learning to generate things, and they can generate amazing photos you might have seen. And so somehow there's some representation is learned, and that representation is close to the data points. So it's done in a very different way, where somebody's trying to suppress, the generator to get to the right place. So it's again another form of like restricting the information.
Yeah. Okay, so the next question we have is about clustering based on latent space. So you use an autoencoder to do dimensionality reduction, find this latent space, and then if you could you cluster in that latent space? Are there any risks involved in this? I think it's true that so just like when you do any kind of dimensionality reduction, you always have to choose how many dimensions to include in your reduced space. But you can always ask, like, generally you sort of want to choose, well, it depends what your goal is. You might want to choose the smallest latent space that captures a certain % of variance in your data, or you may have some other, I don't know, can you guys think of another way to choose? Like, how do you decide how big your latent space is? Yeah, any thoughts on that?
Yeah, you basically look at the performance that you get, right?
Right.
So the first thing that we see when we look at the clustering of MNIST is, wow, we can use it for classification, because look, all figures are all digit classes are so tightly
neatly
clustered,
separated.
but yeah, but it's like, but if we think about the process, what the network is doing, it's doing, so in the case of MNIST, so in tutorial 2, we're basically just compressing, decompressing. So the network is learning to cluster those digits in the best way to reconstruct them with less error, right? When you think about clustering and doing some classification, that's a different objective. So when you have a network that has a classifier, right, on top, so the weights of the network will adjust for classification, which is a different learning objective than compression, decompression. So and so basically, what you could then do is, well, you build your classifier, so a deep classifier, and then you can visualize the before last layer. So where you have your softmax for your classes, then you could visualize that in lower dimension. And then you would probably find your clusters again, but much better separated, because since you are classifying, you want to have them really well separated.
Right.
But for classifying, of course, then you need to have labels. So right. So what motivates your question is, yeah, we want to classify based on the,
Right. That's the nice thing about autoencoders, is you don't need labels. It's self-supervised or whatever. Right. Okay. So our next question is, when should we use CNN instead of ANN/DNN? So I think this is a bit, so at least from my understanding, everything is an ANN, artificial neural network. Whether it's a deep neural network is just someone's opinion and who they're trying to pitch to. But a CNN is something specific. It's a feed-forward convolutional network. And so I think maybe a better, well, I hope I don't offend you, Jiaqi, but I think maybe a better question is, when should you use like a feed-forward convolutional neural network versus like a recurrent neural network, which might be like more realistic?
Or whether we use a convolution or not, right? So convolution kind of facilitates translation invariance of the features. Right? So if you know that a small change in shift in the feature in the input doesn't change your output, maybe you should use a convolution neural network. But the exact location of the feature is really important. Maybe you shouldn't use a convolutional neural network. So I think what kind of invariance you assume to your data is the important factor.
Yeah. So you want to do convolution in the dimension that you want to build invariances on, right? So for vision, that's often like a spatial invariance. But if it was in a different domain, like for an auditory or some other kind of information, you might want to think about how to do convolution in a frequency domain, maybe, or
or time domain, right?
Time domain, yeah.
The CNNs are interesting when there's a lot of intrinsic correlation between your data points. Anyway.
Right.
So the third tutorial, the last exercise, where you've seen that ANNs, they really don't assume any spatiality between the points, right?
Right.
So in cases where there would be some spatiality or some time correlations, that would be interesting to use CNN, because the architecture is embodying that, right? By the fact that you have this smaller kernel, and that you share it all over the image or all over the feature space, as Kenji said,
Right. Okay, so I think we answered that one, right? Okay, so we actually don't have that much time left, so let's see. We have a few different questions. One question which is sort of interesting is like, do we know in the brain where the decoder is? Or is every brain area doing encoding and decoding? That's kind of a philosophical question.
Yeah. So one idea is that cortical feed-forward and feedback pathway already includes encoder and decoder.
Mm.
So for each of the two cortical areas, there's usually a feed-forward and feedback connection. So this closed loop can do a encoder, decoder. That is an idea. Right? So how the models like predicted coding by Rajashrao and Carl Friston take that kind of view. They are not exactly autoencoder, but yeah, very similar.
Yeah, and also when we look at scenes and we're not really aware of it, but it's like the vision system is filling up a lot of things that may or may not be there, right? When we pay attention to something, we are focusing more on that, but there's things that we sometimes believe they are there, like small details in our peripheral vision. And this could be seen in a way as a sort of decoding. It's like you would expect something of this type to be on that area of your visual field, but actually, yeah, it's not.
So where does like inference fit into encoding and decoding? Maybe that's a good question for MT.
Ah, I had my neurons fire when you asked that question. Yeah, I think I mean exactly this is a very nice conversation, right? It's where is the decoder and sorry, yeah. So like it's not necessarily like you see something and you don't try to fill in everything, you know. So it's not really you're trying to do some kind of prediction, but you're not really just doing autoencoding. So I think inference is the most important part because you were trying to get to the representation when the data is given to you, right? So you're trying to figure out what is the probability that some of your, the representation that you have is going to take certain shape given the scene that you have right now. And you have to do this at test time. So, you have seen many things before, but now when you see something, you need to kind of correlate this new information with all the things in the past that you've seen. And you do that through representation. So like in like this kind of latent variable model or like the thing that you had in the course, it's like you're trying to find X and H is sort of fixed. And so finding X is the inference, and you're trying to find whenever a new, time series is given to you, you're trying to find the sparsity pattern for that. And that you will do with the probability of X given, everything that you've seen in the past. Sorry, this might be a little bit technical, but it's perhaps a very important part because H remains constant as the number of data points are increased, but X is kind of changed given the new Y.
Okay, so would you say that encoding and decoding are like steps on the path to inference? Is that like a...
So, and I think encoding is the thing that is related to inference. That's basically what I'm trying to say. But your goal is to find the latent vector X, right?
Right.
And you do that you could do that throughout your life. Like once you learn H, maybe then it doesn't change much, and then you go to different contexts. If you have seen enough data in the world, then you go to different contexts, you give a Y, you find an X, and then that's all you do. So that's inference.
So can I paraphrase that as saying like decoding is something that scientists do, but the brain really only cares about encoding and inference?
Okay.
No? Is that too far?
I cannot really, Well, I mean, in applications like, these matrix factorization things that we were doing back in, 10 years ago with Netflix challenge, they're like a new user come in and a new user will only watch like 2 or 3 movies. Right. And now your goal is to predict like what this user is going to do. Right. And then many users will keep coming in the future and your goal is to do inference to figure out what their preferences are. That's one example.
Yeah. Okay.
You can sometimes do a kind of decoding across the modality. So for example, you can hear some words and imagine the scene, right? So probably in that case, our visual decoders are evoked by the inputs coming from the auditory or language system. So yeah, for imagination, some decoder, even there's no input, can be helpful.
Yeah.
Right. So like so simulation and imagination are kind of decoding. Interesting. Okay, maybe we just have time for like one more question. There's a few here. So there's a question about regularization. It's a bit technical. But like L1 versus L2, but I don't have anything really useful to say about L1 versus L2. Does anyone want to? So then the other question is, are there certain kinds of features or patterns that are more appropriate for autoencoders than other? Are autoencoders better at encoding certain things better than other things? I think that kind of gets back to what Kenji was talking about in terms of convolution. Like, if you know something about the correlation in your data and you can build some of that into the architecture of your network, whether it's an autoencoder or any other kind of network, you're going to get a boost. Like, you're going to get you're going to be able to skip a bunch of training because you're like, oh, I know this already needs to do this. There's like a classic debate between Jan LeCun and Gary Marcus about like how much should you put in the network ahead of time and how much should you just do from training. And so I feel like this gets to that question a little bit. And Jan's position is that if you have enough computational power, you should just train from scratch. And that anything you put in, it may save you some time in the short run, but in the long run, it's going to do worse than just learning from the data. So I feel like that kind of is, I don't know if you guys have any, want to say anything else about that?
Yeah, like it's in, as we insert some domain knowledge into our architecture, we are making the system better for this data, or we are potentially making it better. May not always be the case, but and it's really a trade-off, because then the system will be worse for all data in general, right? Because you're really tuning it for this type of data, but it can be that this tuning, it reflects our understanding of the data, right? And maybe just not tuning it at all, it will eventually find even better optimization over the data. So it's I would say it's mostly a trade-off between training time, but the other aspect, it can also be that if you don't do this kind of tuning, at least to get started, it can be that the model doesn't converge. So it's always, it's not pure science, it's still a bit of an art. So the first thing is to get it to converge, and if you have something that is already converging, so you know the class of models that will converge for these problems, and then really is if possible, just use like the largest thing that will learn and keep on learning, because if it has more capacity, it will probably learn like stuff that you didn't imagine that was in the data. I would say something like that.
Maybe I quickly add a little bit more technical, that there's two kinds of unsupervised learning models that are popular. One is this kind of factor latent representation, latent factor models, and other is like mixture models. And autoencoder is a factor model, so you have this latent representation, and then you have loading, this H matrix that actually maps to the output. And these kind of things are more suitable for doing bi-clustering of the data. So if you're given a matrix of data, so think of like each column as your time series, and it's like how many times you run it. So it's trying to find a bi-cluster, meaning a rectangle in that big matrix. So factor models are usually good for that kind of data, but mixture models are just trying to do clustering. So they were either clustering the columns or clustering the rows. grouping them together by assigning one latent variable. So that is one way to think about which model you want to use.
Mm.
And the deep learning community has always rooted for factor models versus mixture models. There's lots of papers on this.
All right. Well, I think we, because this is a little bit of a short session, we're actually like already out of time. So I just want to thank our panelists for joining us. It was good to see you guys and nice to meet you. And I just want to remind all the attendees that right after the Q&A, you should do your NMA evaluations, and then you will, after that, oh, I got blurry, go to your SuperPod presentations. And this is the last Q&A for Asia, and we're really at the end of a real marathon for all the attendees and all the organizers. So thanks everyone, and yeah, I think we can wrap it up there.
Yeah. So I congratulate all the students for coming to this end of the 3-week course, and I hope you enjoy your presentations of the projects.
Great. Okay, thanks everyone, guys.
Great, yeah, very nice to meet
Bye.
you all.
Yeah.
Didn't get to say hello properly, but maybe some other day.
Yeah.
Let's keep in touch.
Bye.
Bye.
Bye.